In this lesson we're going to look at images. So we've moved on from characters. We're going to look how an image is represented as a series of pixels. Hopefully you know what pixels are already. If not, we'll try to explain them. And how they're represented in binary. Now I've got a series of videos after this which may help that understanding a little better. We're also looking at something called metadata. That's data about data. Metadata occurs in a lot of places. In particular, it occurs in sort of web pages. There's lots of information about a web page that is not displayed on the screen. That's called metadata. And when we say files, also it contains a lot of information that's not sort of in the file to be seen on screen or heard, but a data about the data, and that's where that comes in. And we're going to look at the effect of colour depth and resolution on the quality of an image, on how good it is, and the size of an image file. And when we're looking at this, the size of an image file, that is one of the questions that they tend to ask you on an exam. They will give you the size of a picture, given its width and its height, and how many colours it's using, and they will ask you how big the file will be. So that is something that you need to concentrate on, be confident with. Metadata and the binary, not so much. But we do need to understand a little bit so that we can work with depth, colour depth and resolution. So that's what we'll do in this lesson. There are two main kinds of images in a computer. One is called a vector image, and they're basically line drawings. So when you do a shape on the screen where you put a rectangle on, or a circle, or a line, that's actually a mathematical calculation. So it doesn't really store all the pixels in the image. It stores maybe just the endpoints and a calculation how to get there. So for example, if I've got a line, I only need to know 2 points on my line to be able to draw it. And so the calculation is done, and the data for the line, other than the calculation, is not stored. The other kind of image is called a bitmap, and that's the image that you take with your camera, on your phone, or on a proper camera, or the ones that you tend to download from Google. They're bitmaps, and the difference between a bitmap and a line diagram is that a bitmap is made up of pixels, and really it's just a shade of colour, and the image is made up by having different shades as it's built up. So let's take a look. On the right hand side I've got a zoomed in version of the image with the chips. Now the image on the left hand side, what looks smaller, is it's got some dimensions. It's 1280 pixels wide and it's 768 pixels high or deep. And we say that the resolution is the multiplication of these two numbers. So 1280 times 768 is the resolution. What that works out to be is the number of pixels in the entire image. And what is a pixel? Well, if we zoomed in, and on the right hand side I've kind of given the impression of zooming in as far as I could go until I actually get one solid block of colour, and that is a pixel. Now your TV screen, your computer screen, your phones, they've all got a resolution in pixels. They've got so many pixels wide and so many pixels high. It's a very, very common measurement. Now what I've also got to say here is that although this is 1280 pixels wide and 768 pixels high, that's the size of the image as it is stored. It doesn't mean that that's the size of the image on the screen. So I've got this image here and I've shrunk it down. It's probably only about 400 by 300. So the actual image size is not sort of displayed on the screen all the time. Some of the pictures that you take with your digital cameras, if you've got a SLR camera, DSLR camera, then that would be larger than your screen. And the amount of colours that it sort of has embedded in the picture is really there for printing. You can print out more colours than you can see on your screen. And if you printed out what was on your screen to a printer, it would look a bit grainy. So what you see is not what you get in size or colour. The screens are fairly bad for representing colours. So we need to know a bit about the images to be able to play with them. And in this lesson, we're just going to look at this calculation really and how they're stored. Later on, we'll take a look at colours and what happens with images. So let's just do an example. Here I've got my representation of a very, very small picture. 4 pixels wide and 4 pixels high. That's all. It's just a kind of tiny little dot in the corner if it was on a real computer screen. Now, that's the resolution, 4 times 4. And in fact, I'm going to use that resolution for all my examples now. And we're going to start off with just 2 colours, a black and a white. So here I've got 0 representing white and 1 representing black. If you printed this out on a piece of paper, you could colour it in. That would be black, black, black down the diagonal, and the rest of it you could paint white. Now, because it's only got 2 colours, it's extremely poor quality, just black and white. So if we were trying to represent a scenic picture, some imagery of scenery, then this would just be awful, absolutely poor quality. We need more colours. So as you can see, if we've got 2 colours, we can just use 0 and 1, and that brings us back to the binary. We can use 0 or 1. That would be 1 bit used for each colour. So each pixel would be 1 bit. So the whole thing here would be just 1 nibble. If I use 2 bits for each pixel, so this pixel here is 0, 0, this is 1, 0, 1, 0, this is 1, 1. 2 bits for each pixel. Well, I could represent those because 2 bits is 4, 2 times, or 2 squared is 4, and I get 4 distinct colours. I can choose whichever colours I want. I've just said white, black, blue, green here. And if you had that printed out, then you could do the same thing here. You could colour that one green, blue, blue, white, and you could build up a better quality picture than just black and white, but only just with 4 colours. And 4 colours used to be in the old 1980s computers, so it's not unusual. But that's using 2 bits to represent each colour. That would give us 4 colours. If I sort of extended that now, same 4x4 pixel resolution, but used 4 bits. If I had 4 bits, I could have 16 colours. And I've listed my 16 colours here from 0, 0 all the way up to 4 ones and give them a unique name. 16 colours. Now I'm getting some quality in my image now because I've got a lot more colours, and probably the old-fashioned Mario games on the Game Boy, that kind of thing, but still not brilliant, not good enough to represent an image taken with a digital camera. And the same goes for this one, 4 bits for each pixel. So this pixel here would be 4 ones, that's magenta. The next one across is 1010, that would be turquoise. Then this one would be silver. This one would be white, 1011, that would be cerise. Then 10, that would be orange, and then magenta, and so on. So I could get a better quality, but not brilliant. As the computers got better, I mean 16 colours used to be fairly good for an 8-bit computer, but as they got better, we could actually use all the 8 bits for each pixel. And what I mean by the 8 bits and the 4 bits, that is the colour depth. So this has got an 8-bit colour depth, this has got a 4-bit colour depth, then I had 2-bit colour depth and a single bit colour depth earlier. But because I can have 2 to the power 8, that would give me 256 colours that I could use. Now, I've got to the point where I just cannot sort of repeat 256 colours and give them unique names. I certainly could. There could be a table with that, but there has to be a better way of doing this. And the computer can handle that itself. We don't need to be concerned with it. But if we have 8-bit colours, so this one is 2 nibbles, 1111, 0101, 8-bit colours as my for each pixel. I'm going to get a better quality image, but looking at this, I'm kind of losing the will to live with all of these binary numbers. They're quite hard to read. So this is the same table that we had before, and a better way of sort of giving the colours is to have them as hexadecimal. So this one here, 4 ones is F, and 0101 is 5, 1011 is B, and the 4 ones is F. So I've replaced all of these binary numbers with hexadecimal numbers, and that is the usual way of representing 8 bits as a colour. So we can have 256 colour. Each pixel can be represented by a single bit. Now 256 colours is a better quality. It used to be good enough for some images, and in fact, if you've seen animated GIFs or anything else like that, or memes, then generally they're using 8-bit colours. GIFs are a file type that can only use 256 colours. So any animation that you see on your phone or on the website or on a web page would generally be a GIF, and it would have 256 colours. Good enough for an image, but very, very grainy. So the quality is not as good as we can have. The final one is this one at the moment, where we use 3 bytes or 24 bits for each colour. So you can imagine that are the pixels, and I haven't drawn the table this time because I'd have to write 24 ones and zeros in each box, and I would probably run out of screen. So 3 bytes are there to represent each colour, and the way it's done is 1 byte, 8 bits, is for an amount of red, 1 byte is for an amount of green, and 1 byte is for an amount of blue. So we've got a red, green, blue colour order. But I'm not too interested in the colours at the moment. What I am interested in is sort of the size that this picture could take up on the disk. Now, this picture is 1,600 pixels wide by 873 pixels high, and this is not an accurate representation. It's been shrunk on the screen. It's far larger than this. But what we do have, now that we've got 24 bits for each single pixel, for 1 pixel there, I need 3 bytes of information. The next pixel, 3 bytes of information. I get really high quality images. So we need to be able to calculate the amount of storage space that we would need to save this on a hard drive or on a memory stick or on a CD, any kind of secondary storage that we need. So the resolution is the width times the height, and I've got that here, 1600 times 873. That's the resolution. That's the number of pixels that are in that picture, and each one of those pixels can have 3 bytes, or will have 3 bytes or 24 bits to say what colour it is. So my calculation really is, and I'm going to use 3 bytes here, I've highlighted that in red, is my resolution, which is 1600 by 873, which gives me this rather large number, which would be 1,396,800 pixels. That is a few pixels, but not big by image sizes by any means. So I'm going to multiply that by the number of bytes that I really need for my colour. So the 1,396,800 times 3 bytes gives me this number here, which is 4,190,400 bytes, because I've multiplied it by 3 bytes. Now, that's good enough. I could leave it at that, but generally the exam paper will ask you to give it in kilobytes, megabytes or gigabytes. So generally we're going to convert that to be an easier to read number. So bytes, if we want to get kilobytes, we need to divide this by 1,000. We started this term off by looking at how to convert from bytes to kilobytes and so forth. So if I divide this number by 1,000, not 1024, 1,000, I get the number 4190.4 kilobytes. Now that is still rather a large number, so it would probably be better if I divided this by 1,000 to get the amount in megabytes. And if I divide 4190.4 by 1,000, I end up with 4.1904 megabytes. Notice really I'm just moving the decimal point 3 places each time. So at the end of the day, this picture at this resolution, the width and the height, with this amount of colour, 3 bytes per pixel, I'm going to need 4.1 or nearly 4.2 megabytes on the disk. Now, we could do that and work it out in bits. And when you're doing your exam, be careful how they're presenting the information to you, whether they're giving you it in bits or whether they're giving you in bytes. We end up with the same value, 4.19 or 4.2 megabytes, but we've got an extra step in the calculation if we're using bits. So we still find the resolution, 1.396 million. But this time, instead of multiplying it by 3, we multiply it by 24 because there's 24 bits. And then we get a value in bits. And that is, we never say or store anything in bits. We always store it in kilobits, bytes, megabytes, gigabytes, whatever. So I really need to convert this. And if I divide this number by 8, I get my value in bytes. And you'll notice that my number of bits divided by 8 gives me the same number of bytes as I had before, 4.19 million. And again, dividing that by 1,000 gives me in kilobytes, dividing that by 1,000 again gives it me in megabytes, and it's exactly the same number. So be careful how you're given the information, whether you're giving it in bits or whether you're giving it in bytes. If you're giving it in bits, you're multiplying by 24 and then dividing by 8. And if you're giving it in bytes, you're just multiplying by the number of bytes. And we'll have plenty of practice before the exam on that one. Metadata. Metadata is data about data. We've just seen that we can store 4.2 megabytes. It's just a little bit over 4 megabytes. But actually that's not the actual size of the file on the disk. So if you calculated your picture's width, height and colour depth, you'd probably wonder why actually you needed more space on the disk than your calculation worked out to be. And that's because it stores a little bit of extra information, and I cover this in some videos later. So what also would be stored along with the pixels for the image would be some data about the picture, how big it is, what its dimensions are. It might have who created the picture, so it might have the person's name. It might have the type of file it's got to be. It might have the size of the image. It might have the color depth. It might even have a color table. Different file types store their information in different ways, and they have this little bit of extra data in the file on top of your 4 megabytes. It might be just a few bytes, it might be 100 bytes, it might be a couple of 100 bytes. It certainly wouldn't be very, very large, but it's enough to say that this is not an exact figure when storing the data. It's a little bit more. So there'll be a few more bytes of storage required for your picture, because we also store some metadata about the picture. Again, I'm trying to make that clear in the videos. So the actual file size would be a bit larger than 4.2 megabytes. You could state that in the exam, so you could work out your calculation and give your answer as 4.1904 megabytes plus some metadata. That would be an acceptable answer, but I think they wouldn't mark you down if you just left it at 4.1904. I think they would still give you the mark for that. You won't be marked down for not including the metadata, but be careful when you read the question just in case. So I've produced 3 further videos to go with this lesson, so that you can actually look at how a file is created, an image file and a text file, and see how the binary and the hexadecimal all go together to make that image up, and how you can probably change things. I start off by looking at plain text. That's just words, not Microsoft Word. That is not plain text. I'm talking about things like Notepad or Notepad++, where there is roughly 1 byte per character if you're using ASCII or an ANSI table. It can be different if you're using Unicode, where you might need 2 bytes per character. But you could be asked to work out the size of a simple text file, although I'd be rather amazed if they asked you to do that. But basically it's just 1 byte per character. And then look at how images are stored, and I try to do it from a point of view of monochrome, black and white, show you the files and how the values are stored and where you can see the information about the file size, and then you can probably do the calculation to work it out. Have to be careful though. The exam board and images is just a kind of approximation, because different file types use different ways of storing data, and it might not be 100% this resolution times color depth calculation. There may be tables in there, the metadata might be rather large. But for the exam, really, this is what you need to remember. The resolution times the color depth should always be used in the exam. And notice also that could be 3 things. Instead of resolution times color depth, you could have width times height times color depth, because really width times height is just the resolution. And the only other thing I can say is take care if you're working in bits or bytes. You could be a factor of 8 out, or even a factor of 1,000 now, or even 8,000. So be careful. Read the questions carefully. But we'll have practice before we do that. Hopefully you understood a little bit about images. Take a look at the other 3 videos. There's no exercises for you to do with them. It's just information. If you want to download the software, see me and I'll help you out with that. But be careful, because the software is very dangerous if you're playing with files. So, next lesson we'll start taking a look at sound.